Oh, I gotta get rid of that guy. Gotta get rid of don't save. There we go. All right, so here we are. Um, Now here's a blank screen. Now this is, we're gonna look at charges and fields, just so you get an idea. Here's kind of a big overview of the thing. All right, so I take this one, there we go. That's the electric field coming out of there. That's a 1 nanocoulomb. Let's make it 2 nanocoulombs right there. Maybe 3 nanocoulombs right there. Okay, so we got 3 nanocoulombs. Now, what happens when I take this negative charge here? Well, look at that. The electric field wants to go towards them. And so I can put these field sensors out here. There it is, 2. So notice the electric field is kind of this red coming out of here. This kind of gives us the direction. But if I put sensors along here, there you can see, can you see that even? 29.5 volts per meter. That's a different way of looking at the electric field, but it is a volt per meter. All right, that's its strength right there. There's the strength right here. Probably be able to read that better. 26.3 degrees is the angle, 37.9 volts per meter. All right, now let's bring out this little guy called a voltmeter. Okay, and it's going to show you the equipotential. In other words, I'm going to measure, I'm going to click. I used to be able to click. Oh, I thought I could show the equipotential of the voltage lines. So you can see that they were perpendicular. Well, it's not working. That's the direction only. All right. Well, anyway, you can see that the voltage is getting less and less as I get, it's going negative as I get there, even though it's getting strong. The electric field is really strong right here. Electric field is really strong, 122 volts per meter. The potential is a huge negative. Now watch what happens when I start sliding over here to the positive side. I used to be able to put in voltage rings here, but I can't do that anymore. Notice the voltage is getting bigger and bigger as I get closer and closer to that charge. Now we're up to 122 positive volts. Somewhere in here it's got to go to 0. I wonder where that is. It's getting closer and closer to 0 as we're getting closer and closer. Oh, it flopped right there. There it's very small voltage. But notice it's got an electric field, but it's a very small voltage. All right? These are the types of things we're going to be looking at in this chapter. All right? So let's go back to their slideshow here. Get rid of that for you. Okay, processing done. Oh, I'm showing you how I make my YouTube videos here. Dang it, what now? What? I'm all discombobulated. All right, so here we go. Electric potential energy. I already did the basketball thing for you. Higher potential, lower potential. Same thing with the charge. Higher potential as it gets closer to a bunch of positive charge, lower potential as it gets close to a bunch of negative charge. Now, if this is a positive charge and it's real close to these positive, what's it going to do when you let go? You're right, it's going to go flying down this way. If it's a negative charge, what's it going to do? It's going to go up that way. Okay, so the work done to get the charge from here up to here, the work done to move that charge from here to here is equal to the change in the electric potential energy. Okay? So the potential energy per unit charge is called the electric potential. So it's joules per coulomb. Because this is an energy. So let me make that clear. Electric potential energy is equal to joules per coulomb. All right, it's in joules per coulomb. All right, and so how do we get there? How do we get to joules? How do we get to joules? Well, we've got a force, right? A force times distance, that equals work. Remember that? Well, here's what we do. Then to get the electric potential, the electric potential energy is in joules. All right, the electric potential, the potential difference, or the potential as we call it, the voltage is joules per coulomb. This is joules. That's work. So what do we have? We got charge times electric field. That's the force times the distance. That equals our electric potential energy. Okay? So force times distance, still the same thing. So we also call it Q times V, where V is the voltage. All right? Those are the big ideas. V is the voltage, and V is equal to the electric field times the distance that we moved, the change in distance, or E delta D. Okay? So if you've got Q, E delta D, that equals electric potential energy. If you take the electric potential energy and divide by the charge, you've got the potential difference. Potential difference, which is equal to, we're assuming E is the same all along, it's not getting weaker, E times delta D, which is equal to V, which is a voltage. All right, we kind of went all over the barn there on that one. All right, so we'll stop with that one, and then we'll actually